We're going to get in today and tomorrow really, or Thursday really, talking about acids and bases. And so that's not something we've gotten into really at all before. We kind of know how to name an acid and we know what indicates an acid. What is it that tells us right away that a compound is an acid? That hydrogen, and where is it usually located? In the front, right? Hydrogen usually comes first. And so this is what I'm going to give you. There's two ways we can define acids and bases. And the first of which is as a proton donor and a proton acceptor. And that's called a Bronsted-Lowry acid and a Bronsted-Lowry base. And so that's the definition I want to use. Okay? It's what we're kind of used to seeing is that an acid is a proton donor. And when we say a proton donor, what do we really mean that it's donating? An H plus, right? An H plus, a hydrogen ion, right? Because if it's a hydrogen ion, it only has a proton and no electrons and no neutrons, and so it's just a proton, right? So when we talk about Bronsted-Lowry acids and bases, we're talking about the ability for them to accept or donate a proton or a hydrogen ion. The other definition of acids and bases are called Lewis acids and bases, and they talk more about electron transfer. And so for us right now, Bronsted-Lowry bases and acids are the easier way for us to be able to define them. So this is an example I gave you of a strong acid and base reaction, right? We've got a pure proton and a hydroxide and a base that is going to accept that proton, which forms water. And so that's the relationship we see a lot with acids and bases, is that bases typically carry an OH, right? They typically carry an OH because that OH readily accepts the proton or the hydrogen to become water. Okay, I'm going to give you a list here about what's called strong acids and strong bases. There are two categories of acids and bases: strong acids and weak acids, strong bases and weak bases. And so the difference is that in an acid or a base that is strong, that's considered strong, it dissociates all the way. It 100% dissociates. And so when I say dissociate, I mean when it gets put into water, it completely ionizes. Okay, so it's got like 100% ionization. That's what happens in a strong acid or a strong base. Okay, they completely ionize. So here's our list of strong acids and strong bases. It's not really something I need you to memorize, but a lot of the ones that we use often are on this list. Hydrochloric acid, sulfuric acid, nitric acid, those are ones that we use a lot, and we'll use those in labs a lot because they do exactly what they do exactly what we want them to do, right? They donate the proton every time because they dissociate 100% of the time. That's the difference. That's a part of being a strong acid. And then strong bases do the same thing. They will dissociate all of the time as well. Let me point out a couple things here with our strong acids. 1, 2, 3, 6 of our 7 acids are considered monoprotic. What do you think that means? It's a monoprotic acid. It's got 1 proton. So here's our 6 that are monoprotic. And then what do you think this one might be called? Diprotic, right? So a diprotic acid means that it has to donate 2 protons. Okay, it will donate 2 protons. All right. So here's some definitions that I want you to kind of be familiar with as we get into this method of titration. We're going to talk a lot about titration, and we're going to do a really cool lab with a method called titration. And so what titration is the delivery of a certain amount of volume of something that we know the concentration of. Okay? We know the concentration of, and we can deliver that liquid into a solution in which we don't know the concentration of. All right, and so we use that method to help us find unknown concentrations. Okay, so titrations allow us to find the concentration of unknown solutions. A titration is when we put essentially a known concentration of base in what's called a burette, okay, or burette. And a burette allows us to deliver that base into a container, typically of an unknown concentration of acid. Okay, so we take something that we know about the base, we know its concentration, we know its molarity, and we've got this acid that we have an unknown concentration of. And so by being able to determine how much of that base we put in, we can now do calculations to help us figure out what's the concentration of our unknown acid. We look at mole ratios. We look at the volume of each of these delivered. We look at all of these different factors that go into solving for an unknown concentration. And so that's what titrations are used for. They allow us to find the concentration of an unknown acid or base.
Or like, is the known concentration that you're putting into the acid, are those both the same acids? Or like...
So one is a base and one is an acid. And so the way we know and we use a titration is that we put what's called an indicator into the acid. And that indicator will turn a color when the acid gets neutralized. When enough base has been entered into that solution to now neutralize the whole solution, it will start to turn a color. And so that's how we know we've put in just enough base to neutralize our acid solution. And so from there, we can work through the calculations to figure out the solution or the concentration of our acid. It's really pretty cool. And we're going to do one of those experiments. Okay, it's where we put in an indicator and it turns pink, right? And we try to get it, we try to basically put in just enough base to completely neutralize our acid, right? And so if we put in more, the solution becomes even more darker pink, right? But we've got to make sure that we're looking at, we do just enough to basically get our mole ratios the same, and then we can go from there to do the calculations. But we'll walk through that in a little bit. Okay, sorry, a couple other things. Equivalent points is basically when we reach that point. We reach the point of neutralization, and that means when we convert all of our H pluses or our OHs to water, right? When we take all of those ions that are dissociated in our solution and we're able to convert them to water, and we're getting all of our acids to neutral and all of our base to neutral. That's what's called to be able to neutralize or standardize that. Okay, an end point is when we said we put in an indicator. It's like a liquid. We use something called phenolphthalein, and phenolphthalein turns pink when a solution becomes basic, right? So when it becomes a pH on the base side of 7, then that indicator will change colors. And there's a couple of different indicators you can use, but we use one that turns pink when it becomes basic. And so when we reach what's called the end point, we will see the slightest amount of pink. Right, and that's really what we're looking for when we do a titration. But we'll get to that as we go forwards here. All right, so when we look at acid and base titrations, we're looking at being able to completely neutralize our solutions. And so to do that, we've got to try to get them to be equal. And so we're going to just jump in with some practice here, okay? What volume of a 0.1 molar hydrochloric acid solution is needed to neutralize 25 milliliters of a 0.350 molar solution of NaOH. Okay? What I want us to be thinking about here is that I want us to look at our ratio between hydroxides and hydrogen. What's our ratio between H plus and OH? I think it's 1 to 1, right? Hydrochloric acid will donate 1 proton. Sodium hydroxide has 1 hydroxide available, right? So those are going to be a 1 to 1 ratio. Situations in which it wouldn't be a 1 to 1 ratio is if, let's say, we were using HCl and MgOH2, right? That would be a situation where it wouldn't be a 1 to 1 ratio because I would need to have twice as much HCl to neutralize that. Does that kind of make sense? I would have to have twice as much of this because I've only got 1 proton per molecule. And so I would need to have twice as much of it to be able to satisfy or to neutralize all of those hydroxides. Does that kind of make sense now if you see both examples? Okay. So the first thing I want to do is figure out if this is my information given to me about the base, I need to figure out how many moles is there. Because if I know it's a 1 to 1 mole ratio, I got to figure out how many moles of that I have. So I'm going to set up my molarity equation. 0.350 molar equals moles over, and then what do we got to do with that 25 mils? I have to convert to liters. So I'm going to figure out how many moles there are. Okay, and I came out with 0.00875 moles of NaOH. And so that also means I need that many moles of HCl, right? Because it's 1 to 1, that means I'm going to need that many moles of hydrochloric acid as well. And I know I'm starting with a solution that's got a concentration of 0.100 molar equals 0.00875 moles over liters. And so remember, I'm just going to switch these two places, and I'm going to get 0.0875 liters, or 87.5 milliliters. So now I want you to take a look at this system, okay? We started with only 25 milliliters of our base. Why does it take us 100 milliliters of our acid to be able to neutralize? Right? If it's a 1-to-1 mole ratio, why is it not a 1-to-1 volume ratio? Yep, bingo. My concentration of hydrochloric acid is less than 1/3 of what my concentration of base is, right? So a higher concentration means more ions per milliliter. Lower concentration means more water per milliliter, right? So we've got to make sure that we're paying attention to, does our answer make sense, right? I think it's rational for us to be able to think we've got to use more hydrochloric acid to be able to neutralize. If they had equal concentrations, then we would need equal amounts of our volume. Okay. All right, let's try this one. This says, for the titration of sulfuric acid with sodium hydroxide, how many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid to reach the end point? So we want to completely neutralize. The first thing I've got to do is figure out my moles of sulfuric acid that are present. So I'll take 0.500 molar equals moles over 1 liter. And so that gives me 0.500 moles of H2SO4. Okay, so let's look at our relationship here between H and OH. Are we going to need twice as much sulfuric acid, or are we going to need twice as much base, sodium hydroxide? Twice as much base, right? I'm going to need twice as much base. So I could set up a chart and look at the mole ratio and plug in the mole ratio, but I could just know that I have to have 1 mole of NaOH ions, right? I just have to have that because of this 2 right there. In order to neutralize and use up all of those hydrogen ions, I'm going to have twice as much of my base. All right, so now, actually all it asked me for was moles. So I think I just need 1 mole. Are we seeing that relationship okay? Sometimes it's counterintuitive, right? We see the 2, we think 2, but we've got to make sure that we're thinking about how much is going in and what needs to be used to neutralize. First and foremost, it tells us the mass of our KHP or KH, right? This thing is called KHP for short. It tells us the mass of that. What are we going to have it in inevitably? We got to go to moles. So let's just do that first, right? 1.3009 grams. I'm not going to write it all the way out. We're going to go ahead and find molar mass of that and then calculate our moles. I had it at 204. I don't know if that's similar to what you had. Okay. And so that gives me 0.00638. I'm just going to round it there. Moles of KHP, right? This has a bigger name, but it gets abbreviated KHP. And this right here gets abbreviated KHP. Okay, so with that, we know that's how many moles of our acid are present. And what do we know about the mole ratio between our acid and our base? it's 1-to-1, which means we're going to also need 0.00638 moles of NaOH. It tells us we used 41.2 milliliters to neutralize that. So now all I'm going to do to solve for my concentration is say molarity equals 0.00638 over my volume. And I'm going to put that volume in liters. I'll give you a head start on this one, but I'll put it up in just a minute. But I want you to try this on your own. But I think you need to divide by 2 because I'm going to need twice as much HCl as I am my base, right? So I'm going to divide that by 2. That's okay. I'm just worried I did my math wrong. Okay, now we're good right here because that says 0.5. Okay. Yeah, the reason we have to divide by 2 here is because if I think about it this way, I need twice as much HCl, or I only need half as much of my base, right? So I've got to divide that by 2. So I came up with 5 milliliters. I don't know if that's what you guys had as well. Okay.